Right, back. Limitations of physical measurements, 3.1.2. A lot of stuff about uncertainties and how we take measurements and how we describe those measurements. So whenever we take a measurement, there's going to be a thing called a true value, right? That's what the actual measurement is. We often can't tell what the true value is because we have so many errors in the way that we make measurements. You can have random errors. These are spread from true value in an unpredictable way. The way to get around random errors is to make more and take a mean. So repeat and take an average. Systematic errors, these ones differ from the true value by a consistent amount, same each time. So it might be a 0 error on your balance, or like half of your ruler is missing. You need to repeat these. They're difficult to spot, but you need to repeat them using different equipment or a different method. Precision, precise values have very little spread about the mean. So they're all very similar values. They're not necessarily accurate, they're not necessarily the true value, but they're very close together. Repeatability is if you do the same experiment and you get the same results using the same method and the same equipment. Reproducibility is if a different experimenter repeats using different method or different equipment and still gets the same results. So reproducible results are really the best. Resolution is the smallest change in the quantity being measured that gives a perceptible change. So it's normally the smallest scale division on your ruler, so millimeters, or it might be on your ammeter 0.01 amps, the smallest scale division that actually makes a change. And then accurate results are close to the true value. Difficult to tell what the true value is though. Now, whenever we make results, or take any kind of readings or measurements, there are going to be differences in them, and we cannot be confident that we've got close to the true value. So instead of worrying about that too much, we give our results with an uncertainty built in. Now, an uncertainty comes after the measurement or the reading, and it tells you the interval in which the true value is going to lie. There are 3 ways we can quote uncertainties. We can quote them as absolute uncertainties, so a fixed quantity. So for example, if I was measuring a mass, I might say the mass is 71 plus or minus 1 kilogram. And that plus or minus 1 kilogram is the absolute uncertainty, same units as the value you're measuring. A fractional uncertainty, it's just a fraction of the measurement. They don't have units because you've done it as a fraction. And to be honest, they're not really that useful. They're kind of just an interim to calculating the percentage uncertainty. So the percentage uncertainty is your uncertainty, your absolute uncertainty, divided by your value or your mean value, multiplied by 100 to get it into a percentage. So for example, for my mass that I measured, I would say it would be 71 kilograms. I can write it as plus or minus. AQA don't tend to do that though. They tend to write the percentage uncertainty, and then they just tell you, well, that's 1.4%. And you know that value could be 1.4% higher, which would take it to 72, or 1.4% lower, which would take it down to 70. So that's how we quote in uncertainties, or the 3 ways we can quote uncertainties. Now, whenever we take measurements, we need to decide whether we're taking a reading or a measurement in order to find what the uncertainties are. If we're taking a reading, that means we've just got one judgment, and that will just be half the smallest scale division. So for example, a thermometer or an ammeter, all these things, just one judgment. And so it's just half the smallest scale division. However, if you're taking a measurement, that means it's 2 judgments. So for example, a ruler, you have to line the ruler up with both ends of the ruler have to be aligned. So therefore it becomes a measurement, and it's plus or minus 1 times the smallest scale division. In their handbook, AQA have a list of all the things they deem to be readings or measurements. So you can look that up, right? However, there are some exceptions. So for example, if you're using a stopwatch, it's unlikely to be, and you get, say, you get 30.03 seconds, it's unlikely to be plus or minus 0.01 seconds. It's more likely to be down to your reaction time, so maybe even a second. So they can be larger. In that case, you kind of you rely on some of the other things later, so a repeated measurement or a multiple measurement. So stopwatch, going to have larger uncertainties. If you're trying to measure the length of the wire, it can get kinked. It's not that easy. Multiple uncertainties. And sometimes things like ammeters and voltmeters actually have a manufacturer quoted uncertainty. So it's not the smallest scale division, like half the smallest scale division, but actually they say this voltmeter reads to plus or minus 1% or something. So you've got to look out for those. Now, repeated measurements, if you take a repeated measurement, then your uncertainty becomes half the range, right? And that can help reduce random errors, but it means your uncertainty might be bigger because your uncertainty will be half the range being your biggest value minus your smallest value, obviously after you've taken account and removed any anomalies. Multiple measurements. So for example, you might decide that you're going to, instead of measure the thickness of one sheet of paper, measure the thickness of 10 sheets of paper. Or if you're doing a pendulum, you might count 10 swings instead of one swing. And for this one, you divide the uncertainty by the whole number, so the number of swings or the number of paper. So for example, if I had 10 sheets of paper and I got reading of 3.2 or 10 swings, 3.2 plus or minus 0.1 seconds for my swings, right? For one swing, I just divide both of them by 10. So I get 0.32 plus or minus 0.01 seconds, right? So if 10 swings was 3.2 plus or minus 0.1, one swing, you just divide all by 10. So that can help us reduce our uncertainties taking multiple measurements. Now, if also sometimes we get given values. So for example, on the front of the data sheet, you've got lots of values like the mass of an electron, the speed of light. For given values, we assume that the uncertainty is plus or minus 1 for the last significant digit, right? And that in general is the link between uncertainties. The uncertainties and the last significant digit tends to be, so the uncertainty tends to be plus or minus 1, the last significant digit. Right, next bit, combining uncertainties. So if you're, say, measuring potential difference and you're measuring potential difference by calculating current and resistance, you need to combine the uncertainties in the measurement of current and the measurement of resistance. If you are just adding or subtracting things, which is rare, but if you're kind of doing a length minus a length, you just add the absolute uncertainties. Even if you're subtracting, you add the absolute uncertainties. If you're multiplying or dividing two values, like the example for current and resistance to find potential difference, you add the percentage uncertainties. If you're raising to a power, well, I mean, that's just multiplying. But if you're raising to a power, you multiply the percentage by the power. So if you're doing something cubed, the percentage uncertainty gets multiplied by 3. But again, that's just because you're really multiplying it 3 times, and so you're just adding it 3 times together. So not necessarily different. Right, so that's how we combine uncertainties. Now, once we've got uncertainties, we can plot them on the graph as error bars. So when we do error bars, we plot a mean value on the graph. Now, you plot your points as little x's, right? Or pluses if you have to, but x's. Then you know your error in your value, which is normally half the range. Most of the time you've got repeated measurements, but it might be you don't, you've just got one judgment, and so it'll just be the smaller scale division. So you draw a line up on your error bar going, and this value here will be half the range. So, and then you draw a line down and that value is also half the range. So this value here is half the range. And what you're saying then is really this point could be plus half the range, so it could go all the way up to here, or it could be minus half the range, so it could go all the way up to there. You can also have error bars on the y-axis, but they don't tend to do that. I don't think there's been any examples of that yet. So that's how you draw your error bars on your graph. So when you plot a graph, you might get a situation like this. We've got a couple of points with error bars, and you want to find the gradient, maybe the y-intercept. So when we find the gradient, the first thing we're going to do, don't have a ruler, I've got a compass, which is a bit weird, sorry. So the first thing I'm going to do is I'm just going to calculate my regular gradient. So I'm trying to go through as many points as possible, but have points above or below the line, like that, right? This is a straight line. So that's going to be my best gradient that I've determined. However, I actually can see that actually the points could have been shifted differently. This point could be down at the bottom, that point could be at the bottom, that point could have been up there, that point could have been up there. That's what my error bars tell me, the maximum and minimum areas the points are. So my gradient could never go out of those error bars because then, well, that's what I've said the maximum and minimum is. But actually, you can see I could draw a gradient that went like this, and I'm still going through all the error bars, so it's still valid, but it's going to be much higher gradient because it's a steeper slope. So this is going to be my highest, worst gradient. I mean, it's not a good gradient to plot, right? It's miles away from the points, but I'm still going through all those error bars, so it is possible that that could be the gradient. And on the same way, I can do, this is going to be quite a steep one, so I can, quite a shallow one, so I'm going to do another one here, and that's going to be my lowest, worst. Right, so I've drawn the lowest possible gradient there. And you can see I've also done the y-intercept. So I've got my best y-intercept there, my highest worst y-intercept, and my lowest worst y-intercept. You then need to figure out which of your worst is the biggest difference, the furthest away, right? So is that the difference between that biggest or the difference between that biggest, and you find your actual worst value, so the furthest away value from your best one. You can then use that to find the uncertainty in your gradient or your intercept by doing the best minus the worst as a modulus value. So this always needs to be a positive value. We don't ever want to get negative values for uncertainties, for percentage uncertainties. They're plus or minus anyway. So the best minus the worst, but as a positive value, divided by the best value times 100%. And you plug those in and you should get your uncertainty in your gradient if you've used the best minus the worst gradient, or your uncertainty in the y-intercept if you've used the best minus the worst y-intercept multiplied by 100. That's it. That was a big one.